So we've kind of looked at the pieces of hypothesis testing and what we need to do it. We haven't actually done a full hypothesis test yet, so we're going to do that today. Things that we need to test a claim about a population proportion are a simple random sample, a binomial distribution where it meets the requirements, two possible outcomes, independent, fixed number of trials, and probability of success remains the same on each trial. We also need basically to ensure that our sample size is large enough, and that comes from having information that tells us n times p is greater than or equal to 5, and so is n times q. So if we look at this one down below, we're talking about a claim that 50% of adults have never flown on an airplane. So checking to make sure it meets these requirements. Yes, it says it's a random sample. It is binomial, yes or no. We have a set number of people we've polled, and if we take n times p and m times q, those are all greater than or equal to 5. So we can test this claim. First, let's figure out what our null and alternative hypothesis are. Always start with what's being claimed, because this is really going to help you with your wording later too. We're claiming that p is equal to 0.5. The other situation we could have is really maybe p is not equal to 0.5. So since our claim involves exactly our equal sign, it's going to be our null hypothesis, and the other cases are alternative. We need our test statistic, so let's plug in our values into our formula. We're going to have 0.47 minus 0.5 all over the square root of p is 0.5, which means q is as well, and then our sample size is 1,125. Be sure that you try typing this into your calculator and make sure you get negative 2.01 so that you know how to type it in correctly. For our critical value, we need to look at our significance level and our alternative hypothesis. So our significance level, alpha, is 0.10, and our alternative hypothesis is not equal to, which means we're going to take that 10%, split it in half, and put it in each tail, because we're rejecting our null hypothesis if it looks like p is either greater than or less than 0.5, because it's a not equal to. So in either case, we'll reject our null. Means our critical value, if you look at your normal distribution table, is going to be positive and negative 1.645. We'll reject our null if our test statistic falls into either one of those regions. So if we compare our test statistic of negative 2.01 to our critical value and critical region, we just got a test statistic that falls within that critical region, so we will reject our null hypothesis. Now, when you make your initial conclusion from a hypothesis test, there are really only two conclusions that you'll be making. You are either going to reject the null hypothesis, which also means you'll support the alternative instead, or you're going to fail to reject the null hypothesis. So there's either enough information to reject your null, or there's not enough. Now, reject the null hypothesis basically means nothing to anyone who doesn't know statistics, so you're going to need to reword your conclusion in non-technical terms so that it makes sense to the normal average person. So if you're going to reword your conclusion, it always is about answering what was the result of my original claim. So we want to word it in terms of what our original claim was. So there is a handy-dandy chart in your book, which I don't really use because I'll show you how to do it without the chart. And if we get back in school, I do not give you the chart on tests or quizzes. So this is just kind of a like, hey, for example, while you're getting started to check yourself sort of thing. So if you follow this flowchart, it asks, does your original claim contain an equal sign? That would be yes for us. Did we reject? Yes, we did. That means there is enough evidence to reject our original claim. I just would recommend that you work on not using the chart. So if you look at what we did, we rejected our null hypothesis. Our null hypothesis corresponded to our original claim. So what are we going to do with our claim? We're going to reject our original claim. So if we word this in terms of restating the question, what do we actually do, which, yes, you have to do, what we're going to say is there is enough evidence to reject the claim that 50% of people have never flown. So we're going to work on our wording. Here, the claim is that the percentage of people with blue eyes is less than 30%. And that would mean that our other situation could be maybe p is greater than or equal to 0.3. So if we convert these to our null and alternative hypothesis, our null hypothesis is going to be p equals 0.3, coming from our other case. And our alternative hypothesis is going to correspond to our claim. Says we have sample data that says we're going to reject our null hypothesis. So we're rejecting H0. And we're always trying to determine what that tells us about our original claim. So our original claim isn't our null hypothesis, it's our alternative. If we're rejecting our null hypothesis, that means we're supporting an alternative instead, which is my claim. So I can say there is evidence to support the claim that the proportion of people with blue eyes is less than 0.3. And yes, I know it feels like English class, but you really should reword everything in terms of the original claim. Let's look at a different one. Here, it's claiming that the proportion of four-leaved clovers in a yard is different from 3%. So not 3% of your yard is four-leaf clovers, is their claim. So if we write this out, our claim in our other case, and then find our null and alternative hypotheses. Our null is going to come from our other case, and our alternative is our claim. So it says sample data causes us to fail to reject the null hypothesis. So we don't have info to cause us to reject our null hypothesis. In terms of what that means about my original claim is if I can't reject the null, I don't have evidence to support an alternative instead. So I don't have enough evidence to support my original claim. So we're going to say there is not enough evidence to support the claim that the proportion of four-leaf clovers in a yard is different from 3%, which I'm running out of space, so I'm just going to summarize it here a little bit. Okay. A reporter claims that 65% or more of people change careers at least once. So claim is that p is greater than or equal to 0.65. Other situation is p could instead be less than 0.65. Null and alternative hypothesis. This time my claim does correspond to my null hypothesis. And the other case is my alternative, p is less than 0.65. Data is causing us to not reject the null hypothesis. So if you look at what that means about my original claim, well, my null hypothesis this time corresponds to my original claim. So saying I'm not rejecting the null hypothesis is the same thing as saying there isn't enough evidence to reject my claim. So there isn't enough evidence to reject the claim that 65% or more of people change careers at least once. Now, people always ask me, well, I'm saying there's not enough evidence to reject it. Isn't that kind of saying that I support it? Not exactly. Saying there's not enough evidence to reject something doesn't necessarily support the fact that it's true. I just don't have enough info to cause me to reject it, so it's a little bit weaker. Okay, my next one is the same situation, except I changed my sample data a little bit. Actually, I need to change my sample data. So same situation. Let's say that I do reject my null hypothesis. In terms of my claim, since those correspond to one another, I am going to say that I do reject the claim that 65% or more of people change careers at least once. So even if we go through and conduct a hypothesis test, sometimes our conclusion can be wrong. We can never be completely 100% confident in our conclusion. So there are two main types of errors. First one is a type 1 error. So type 1 error is we reject the null hypothesis when it's actually true. And the probability of that happening is whatever our significance level is. So if we're using a 10% significance level, there's a 10% chance that we reject the null hypothesis when it is true instead. If we put this in context of an actual situation, like in medical testing, let's say that our medicine's being tested, which means the null hypothesis is going to be that the medicine does not change the outcome of your disease. If our type 1 error happens and we reject the null hypothesis when it's actually true, we're going to be saying that the medicine does help the disease when in fact it doesn't actually. So that could be pretty serious. So a type 2 error is where you fail to reject the null hypothesis when it is actually false. So in that same medical example, if I fail to reject my null when it was actually false, that would mean essentially that I wouldn't conclude that my medicine would help people when it actually would. So neither a type 1 nor a type 2 error is ideal, obviously. People tend to say that a type 1 error is a little bit more serious.